In this video, we will take a look at properties of the discrete time Fourier series. The spectral representation of a periodic discrete time signal is given in terms of its Fourier series representation. So in other words, we express our periodic discrete time signal x of n as a sum of harmonically related complex exponential signals of the form e to the j k omega naught times n. In fact, this linear combination involves a finite number of terms. There are only n naught terms, where n naught is a fundamental period. The Fourier series coefficients ck are then given by the following expression shown over here. In general, ck will be a complex number, so the magnitude of ck will define what's referred to then as the magnitude spectrum, whereas the angle of ck will define what is referred to as the phase spectrum. The two relations over here give us what are referred to as our synthesis relation and our analysis equation. The analysis equation allows us to extract the Fourier series coefficients from our signal x of n, whereas the synthesis relationship tells us how to reconstruct our signal x of n based on the Fourier series coefficients. There are no convergence issues with the discrete time Fourier series, since any periodic discrete time signal will be completely specified by a finite number of terms. In other words, the synthesis relationship shown over here will always be summable because we are only using a finite number of terms in the summation. This is in stark contrast to the continuous time case, where, in order to reconstruct our periodic continuous time signal, we actually have to sum up an infinite number of complex exponential functions. And this can give rise to convergence issues. Many properties of the discrete time Fourier series are similar to those of the continuous time Fourier series. Let's consider the following discrete time Fourier series pairs. So periodic discrete time signal x of n has Fourier series coefficients ak, and periodic discrete time signal y of n has Fourier series coefficients bk. If we consider the product of x of n and y of n and want to obtain the Fourier series representation, then we simply have to obtain the convolution of the Fourier series coefficients of the individual discrete time signals. On the other hand, if we multiply the Fourier series coefficients of the two discrete time signals, then in the time domain we simply have to perform the convolution. If we shift the signal in time by value n naught, we simply take the Fourier series coefficients and multiply it by e to the minus jk omega naught times n naught. This represents essentially a phase shift on our original Fourier series coefficients. We also have the first difference operation. In other words, if we take x of n minus 1 and want to obtain the Fourier series representation of this signal, then the Fourier series coefficients are going to be given by our original Fourier series coefficients of x of n multiplied by 1 minus e to the minus jk omega naught. This is similar to obtaining the Fourier series representation of the derivative of a periodic continuous time signal. The average power of a periodic discrete time signal is defined by the following sum. But rather than evaluating this sum directly in the time domain, we can actually make use of the Fourier series representation. And in particular, we can show that the average power is then going to be given by the sum, k going from 0 to n naught minus 1, of the magnitude of the Fourier series coefficients squared. So the sequence of values magnitude ck squared is then referred to as the power density spectrum. And calculating the average power making use of the power density spectrum is effectively known as making use of Parseval's relation. If you have any questions, please send me an email.